Claudio. So, good morning, everyone. Welcome to this first webinar of the EXCELLERAT series on opportunities for collaboration around HPC, HPDA, and AI. This webinar series aims to showcase the expertise and ongoing work of the EXCELLERAT technical partners to strengthen our community interactions and to further leverage the Castle2 and EuroCC networks, including the connection with the NCCs. Here, the idea is to create a space where EXCELLERAT technical partners can present their key focus areas to the broader communities while opening the discussion to external stakeholders and explore new collaboration opportunities. So if any other technical partner is interested in participating in this webinar series, please don't hesitate to contact us. Today, for the very first session, we are focusing on interaction with the industry, and we are welcoming our colleagues from CINECA. We have two speakers today. First, Claudio Domenico Arlandini, leader in HPC and AI, who is serving as project manager at CINECA. He also acts as outreach manager for the Italia AI Factory and the Minerva project, driving industrial innovation. With a PhD in astrophysics, he specializes in simplifying complex technology for business growth. And his work earned him the HPC Innovation Excellence Awards. The other speaker is Simone, who holds a PhD in nuclear engineering and specializes in numerical methods and advanced simulation, particularly in CFD and fluid structure interaction. At CINECA, he manages a range of CFD services spanning from numerical modeling to scientific visualization by leveraging open source tools like OpenFOAM for both private and EU-funded innovation initiatives. So the agenda for today will be, we will have a first talk from Claudio on general overview of CINECA and its interaction with the industry. And then Simone will give us a presentation on technical aspects. As a reminder, this session is recorded and we will have a Q&A session at the end of the talks. So if you have any question, please write it in the chat and we will take them afterwards. So, Claudio, if you're ready, the floor is yours.
Merci, Andrea, and good morning to everyone. So I will share my screen. So now you should see my my slides. So the idea is to give you just a brief overview of the whole ecosystem for innovation that we set up at CINECA, and where EXCELLERAT is a key brick of it. So essentially, what is CINECA? CINECA is a public entities consortium, is no profit organization, and it was born in 1969. So what does it mean, the public entities consortium? Essentially, we are gathering all the public universities in Italy, and then 2 ministry and 49 research centers at the moment. We are divided into 6 sites in Italy. We are in total more than 1,000 staff, but I am from the high performance computing department. The high performance computing department is only 200, more or less, people of this 1,000. And if we talk about our department, what is it exactly? What we're doing is essentially a center for competence and innovation. We are providing a world-class computing infrastructure, and at the moment, our top computer is Leonardo, is number 10 in the world top 500 list. We provide technological expertise in HPC, quantum, and AI. We are installing, for instance, 2 quantum systems in our data center right now. And we provide for the researchers and industry access to the European and international ecosystem. How we are targeting industry. Being a no-profit consortium, essentially we are a champion of open innovation. In the sense that the open innovation is our preferred way to interact, and we are doing it with the help of EU-funded projects like EXCELLERAT, with collaboration agreements for public good in some very special and strategic case. We are doing it with a lot of training, and we also provide commercial services if industry is interested. But let's start about, say, the most important for us way interactive with industry, the one with projects. We are essentially part of the European ecosystem about HPC. So we are one of the hosting entity of the EU HPC joint undertaking that is building a sort of pyramids of connection with HPC system in the whole continent, and Leonardo is one of the pre-exascale system. This 250 petaflop of power. But now an important addendum to this strategy arrived that are the AI factory. So CINECA is also the coordinating partner of the Italian AI factory, Italia. It is one of the 19 selected AI factories that are an ecosystem that is built around AI optimized supercomputers, and we are completing our procurement with for this system that will stay alongside Leonardo and will be devoted only to artificial intelligence and to develop the skill and the knowledge on domain AI in Europe. So essentially, to support innovation, we have 3 main channels. First one is the access to computational resources. The second is support, and then there are also some way to obtain direct financial support to industry through cascade funding. So the access to computational resources is the easiest part. So the capability now available in Europe is very large. So we can provide accesses on computing hours on HPC system, cloud system, the new AI factory, and quantum computer system. We have Leonardo is the major system, but we have different type of architectures for every, say, type of applications. And the main way to obtain access for free of charge to Leonardo and the other system is using the EUHPC JU calls. And for Italian research and industries, there are other channels, but EUHPC is the major one for all of Europe. Well, the technical support is provided through some specialized projects, and EXCELLERAT and the other Center of Excellence are one of those. And then we have also 2 projects that are essentially a support, and that while Center of Excellence are devoted to a specific field of knowledge of research, like EXCELLERAT is focused on high performance exascale engineering. And we have 2 projects, the Minerva and Epicure, that are the support center for all Europe, available for every kind of research. Minerva is focused on AI application, and Epicure all the rest and simulations. And then for at the Italian level, we also a number of European digital innovation hub projects that support the digitalization of Italian SMEs. There's also one very interesting project that was funded by the JU, this Fortissimo Plus. This is the fourth generation of the Fortissimo project. It was started, say, 12 years ago, I think, in this family of projects. And along the years, hundreds of European SMEs received funding, and we are talking about for every industrial project for the companies, there is a budget of 200 to 300,000 euro. So this FH Plus is opening regular open calls for business experiments devoted to HPC, AI, and big data, and innovation studies for generative AI. They are very popular projects. But now, when we are talking about industrial support, say our main workhorse is the Italian AI Factory, Italy for Artificial Intelligence, Italia in brief, that is focusing on the three pillars: AI for science, AI for public good, but especially for AI for innovation. Inside this project, we are providing services all alongside the AI, say, project life, starting from the data-related services, so how to make the data in a company AI ready, to horizontal services about model, for instance, creative inference, and the training, skill development. But we have also some verticals with specialized partners, specialized data sets, and specialized pipeline. For Earth, considering Earth, this Earth observation, but also weather, meteor climate, cybersecurity, manufacturing, and agri-food. And the other channel, but is quite rare, are strategic agreements for public good. This was made in a very specific case, like, for instance, the development with some research team in Italy to develop early alert services for extreme meteor events, for instance. And then we have an important focus on generally on training. On training for, when you talk about industry, we are offering 3 courses for industrial researchers. This is done inside the European projects we are in, especially UOCC, the Italia Factory, and Minerva. They are delivered also in collaboration with known EU experts. That are courses that are being taken both online and in person. And in person, we are trying to do it as more geographically distributed as possible. And then there is also the possibility inside some projects to organize ad hoc courses. These are essentially one of the service things that they are essentially prepared just for a specific company, like, for instance, the iFactory and digitalization apps. Then, if you don't find anything that's suitable for you on the free side, you can also buying our services. We have a price list offering both computing services, both on the HPC system and cloud, and say humans, so consulting, support consulting, training services. In this cover very shortly all the effort that we are doing in CINECA for industries. And so I leave the floor to Simone that will talk about a very specific success story. Thank you very much.
Thank you very much, Claudio. Simone, the floor is now yours.
Let me switch on my webcam. Okay, I'm going to share my presentation. Share. Okay. Do you see my screen in presentation mode?
Perfect. Yes.
Okay.
Perfect.
This presentation is more technical than the presentation done by Claudio, and we will talk here about a success story that where I work with my colleagues Ettore and Giuseppe and Tommaso more than 1 year ago about the simulation of a steam axial turbine stage on GPU. Let's briefly see the agenda of this presentation. We start with an introduction and motivation about this work, why we ask money we ask person months to collaborate with a company located in Italy. We briefly introduce Spuma, which is the GPU porting of OpenFOAM that we developed here in CINECA and that we released more than 1 year ago. The third step, we talk about which developments basically we made in this project and the performances we get on an industrial test case provided by the company. And then we draw some conclusions of this work, which is not is a preliminary work to our making complete simulation on GPU for steam turbines. Okay, as an introduction, okay, we just talk about the customer, which is called Depreto Industrie, which is an Italian company located in the north of Italy that produces steam turbines, design and produces steam turbines, and also make the maintenance of them during their life. So this presentation focuses on the simulation of these machines, which are basically turbo machinery that operates with a compressible gas. Okay, and we try to compare the performances of the simulations run on CPU using traditional hardware, okay, and using OpenFOAM standard, and the GPUs using Spuma in order to use the characteristics of modern heterogeneous HPC system. Because as Claudio showed in his presentation, we reached the exaflop barrier thanks to the GPUs. But OpenFOAM in its standard flavor runs only on CPU. So this is why we will see in the coming slides what Spuma is. For turbine simulations, we need to face some complexities, which are basically three. We have to cooperate with this stator-rotor interaction because we have some parts that are fixed and some parts that are moving. So the stator is fixed and the rotor is moving because we have these interfaces that doesn't face each other for the entire simulation. Then we have flow compressible with high speed, because you know it's not easy to manage. And then we have also all the part related to the thermophysical modeling of the steam. Okay, steam in particular is superheated in some part is wet. So it's complicated also on this point. Motivation of this work. We decided to use OpenFOAM because OpenFOAM is one of the most used open source CFD software. So it means that the code can be downloaded for free. There is no fee to pay. And for the Pareto, which is not a so large company like Siemens, they decide to stay with an open source software. So you don't have to pay nothing about fees, and you can use the resources you want, also for GPUs. But for turbo machinery, there are some implementation that are not included in the OpenFOAM itself, but you can find in third-party separate contributions. So you need experienced developer that make all the things all together to run simulations on for this kind of devices. So because you need to take OpenFOAM vanilla as itself and add some features that are not included into the default release from different parties, make it all together, make it working. So this requires a lot of experience. CINECA is not a company. It's not a company that the target of CINECA is not to make simulations only for turbo machinery, but we are an HPC center, so our competence in particular is on exploiting our hardware. Okay, so the effort we made, so the person months that we made here is basically in porting all the features for running turbo machine simulations on GPU using our SPUMA framework. Okay, let's have a look at this picture. So you have, this is only a portion of a turbine, because you see basically only one blade here for the stator and one blade for the rotor. Okay, the gas enter into the stator inlet, okay, flow around the blade in the stator part. So this is the part that it is not moving. And then the flow enters into the rotor inlet, which is moving, or is rotating, and then exit from the rotor outlet. In order to simulate this complex machine, you need this kind of features that I reported here. There are, yeah, I know, some technical stuff, so you can, if you're not an expert of this, you can ask or you can Google or look at the documentation of OpenFOAM. So the first one is the AMRF, which is stand for moving rotate frame. So you need a technique to say consider the rotor fixed by taking into account the centrifugal forces. Then you need an algorithm that, in order to match, okay, in order to manage the exchange of mass and momentum and energy at the interface between the stator, which is fixed, and the rotor, which is moving. And we have two basically way of doing this. One is called mixing plane, and the other one is called overlap AMI. Then you need to consider also the thermophysical properties of the steam, because now your steam enter into the machine, which is superheated, and then at the final stage is basically wet steam. The two solver we use are basically the transient one. This is called in OpenFOAM raw simple form, and the last part we also only in the final part of this work we will also move to the transient solver, which is called raw simple form. As you see from the picture here, the area of the exit of the stator is not completely overlapped with the rotor inlet. And you see here there is a gap. Okay, this requires a a particular way of handling this. This is what, and this is managed by the mixing plane over overlap AMI. Okay, so the final goal was simulating. This is what the request, the target provided by companies, to simulate the last stage of this axial steam turbine, where the steam operates in wet conditions. So we need basically these third-party features that are not included into the OpenFOAM vanilla. The first one is the mixing plane, which is provided by Turbo WG. So this is the source code is open source, but is basically maintained externally. So it's not maintained by the company of OpenFOAM, but this community, Turbo Machinery, which is managed by Hakan Nielsen. Then we have this library, it's called XFOAM, which is developed by a PhD student more than 5 years ago, basically for simulating turbo machinery using coupled solver, density-based coupled solver, and they released also this overlap AMI. And then there is this solver called wet steam foam, provided by a professor, I don't know if it's Czech Republic, or it's professor that released this solver form simulating wet steam. Okay, so what we started basically by combining all these third-party features and make it working into OpenFOAM. So it's a sort of integration and bug fixing work. This is what we done at the beginning, starting from CPU simulations only. Okay, because as I said before, OpenFOAM vanilla doesn't run on GPU. Okay, if we want to make it running on GPU, we need to use the framework we developed in CINECA, and for copyright reasons, we call it Spuma, which is the Latin translation of foam. What Spuma is, okay, this was already explained here a little bit. Spuma is basically a portable and minimally invasive GPU porting of OpenFOAM. There is a paper published on Computer Physics Communications that was released more than a month ago. So you can, if you are interested in this porting, you can download the paper and take a look at the technical details. Here, I don't have too much time here to talk about Spuma. Just I want here that to explain how we arrived, which is the roadmap. Okay, where we start and where we arrive. So if you look at the literature, there were a lot of attempts in the past, basically starting from 2010, basically the first one attempts. Okay, but was limited. In particular, the first attempt only taking into account the linear algebra part of OpenFOAM, leaving the assembly of the matrices still on CPU. CINECA recently during the EXAFROM project, which started in 2020, we get financial here to basically to develop and to release a GPU porting of OpenFOAM. So at the end of this project, EXAFOAM, we released a proof of concept, which we call it ZFOAM, which is a proof of concept that show that it's possible to gain, in my opinion, some interesting performance gains. Okay, but it was released as a plugin for OpenFOAM, so it's it's not basically, doesn't modify anything of the core itself. This is an issue because you need to basically rewrite a complete new rewrite a huge number of classes. So we after this proof of concept, we go to Spuma, which requires more than 1 year of development. Spuma basically is a modification of OpenFOAM. in some core parts, but now is production ready. So it can target a hybrid cluster, can run on GPU. Here there are also some characteristics of Spuma, which is as a minimal code impact. It's very basically we touch few classes and in few points. There are, I don't remember, no more than thousands of lines of modifications. There is an efficient memory management using memory pools that are not included into OpenFOAM Vanilla. The memory pools are needed for running fast on GPU. We don't use any third-party frameworks. We use NGX, which is in an algebra package provided NVIDIA for comparison, but you can run Spuma on GPU without any third-party frameworks. And it also vendor agnostics. At the moment, we tested Spuma on NVIDIA and AMD GPUs. So we tested basically on Leonardo and Lumi, which are the two pre-exascale cluster. One is NVIDIA based and the other one is AMD based. Here there are some slides regarding the performances for an incompressible test case, which is called Rewire. Is a very famous test case for automotive. It's a sort of study, a simulation of the flow around a car with a car which is a representative of a modern car. And here we compare basically the GPUs versus CPU. So this simulations done on CPU from 2000 core to 1600 cores for a case with a mesh of 236 million cells. And we regarding the GPUs, we started from 8 to 24 GPUs. Okay. What we found is that for incompressible cases and for mesh of this order, so we are talking about hundreds of million cells, okay, we found that one GPU is equivalent to 220 CPU core. The comparison is done using the GPU of Leonardo, which are NVIDIA Ampere A100, compared to the CPU of Leonardo, which are Intel Sapphire Rapids. And there is also an important point, which is the reduction of the energy consumption, which is more than 80%. In the paper, you found more detail than this. Here are other technical stuff regarding Spuma. Okay, so as I said before, now we need to basically manage the memory issues. So this is why we introduce the memory pool. We decide to, let's say, perform a gradual development, a gradual porting, because you can, OpenFOAM is a very huge code, more than 4 million lines of code. So we need to find a way of porting features step by step and not in a single way, at a single moment. And so we decide to rely on the unified shared memory, which is the characteristics of GPUs from more than 8 years, I think. Then we need also to modify many algorithms that are completely serial in OpenFOAM, and we introduced the executors, which is a sort of C++ pattern to manage this. And also, as I said before, we decide not to use any particular framework. So we are vendor agnostic. Okay, so we basically introduce many backends, one for each kind of hardware. Okay, so the moment we develop only two for NVIDIA or AMD, but we can add new ones. For example, one for Intel, or I don't know which other we will see in the future. Okay. Yeah, this is probably a very complicated stuff, but I try to be simple as possible. The main objects in OpenFOAM are called fields, or geometric fields. So basically, all the objects in OpenFOAM are put on GPUs on our memory pool by default. So the user doesn't care. Also, the developer doesn't care about this. The unified shared memory, which is a characteristic of modern GPU, make the copy between CPU and GPU in an implicit way. Okay, so if one during the development forgets, okay, to port to GPU some parts of the code, okay, what you see is that there are page faults and there are migration that slow down the simulations but not crash the simulation. Okay, it can happen that since OpenFOAM use some I don't like too much sort of mixed way of using fields and lists, and since the lists are not completely put on GPU by default, here there can be some crash if the lists are not on GPU via memory pool. So here the developer needs to intervene and explicitly put on GPU the list that requires to be put on. But these are very complicated technical details, so I don't want to spend too much time here. So let's move to the application part. So stimulating a steam turbine on GPU. So here we have this our axial turbine. As I said before, we are in the low pressure stage where the flow is wet. We are operating in real conditions. We have a very high Reynolds. The flow is transonic and fully turbulent. Okay, we use OpenFOAM, which is a finite volume second order solver, and the mesh size, which is for this for the picture that you see here, is more than 20 million cells. It's not a very huge mesh. It's only this, but it's sufficiently enough refined for the two blades for running run steady state simulation. As I said before, we need to require this algorithms, MRF, thermophysical model, mixing plane, and overlap AMI. So if you want to perform this simulation on GPU, we need to port to GPU also this stuff. And this is an example of, for example, porting to GPU the MRF, the moving rotate frame, using the SPUMA approach. Okay, OpenFOAM normally use this macro called for all. It's a sort of macro that stands for a classical C++ loop. Okay, the SPUMA approach is basically this one, where you have an explicit loop that runs on CPU only. You need to wrap the loops into a lambda function. Okay, it's a sort of lambda expression. You need also to copy the pointers. Okay, this is automatically done by this equal operator, and then you pass this lambda function to the correct executor, and also you need to use the correct method of the executor. In this case, it's the parallel for this kind of algorithms. So basically, for this simple loop, the SPUMA developer task is just to take the explicit loop, wrap it into a lambda function, and then pass it to the right executor. Then we move to the overlap AMI part. Okay, as I see in the picture before, now we are simulating only one blade. Okay, but in a turbine you have basically a lot of them in order to have a sort of circumferential area. Okay, so as is before, we have this stator part which is fixed and a rotor which is moving, and we need a way of making a way of connecting the interfaces of the stator with the interface of the rotor. And in OpenFOAM, we have this in the XFOAM library, we have this algorithm called overlap MI, okay, which can be used. Since also the domain are not completely overlapped, because you see, the stator doesn't have the same number of blades as the stator, we need this, we need to perform, use this approach. Basically, you need to expand, okay, one blade circumferentially, okay, in order to have this circular, annular circular, okay, and both for the stator and for the rotor, and make an interpolation. Make an interpolation in the surface, and this interpolation is done into this object. Here, this very complicated stuff. I don't want to too much spend time here. Just to show you here that these algorithms cannot be ported as it is on GPU. These require a little bit more of modifications. For example, you need to port this loop, which is now here inside. Okay. Now is for this case is for in the GPU is for outside. So this, let's say, a loop over the patches that need to be copied in order to have this circumferential area is put inside, and this loop over the faces of a single patch is moved outside, just to make it running efficient on the GPU. So this is a little bit more complex than the previous stuff, but it works. And with a single kernel on GPU, this runs fine. This is a picture of the daily work of a Spuma developer. If you, let's say, try to run it as it is by downloading from the XFOAM repository, you see there are, using the NVIDIA profiler, a lot of page faults, okay, that slow down a lot of the simulation, but doesn't crash it. So you can see, for example, which parts, okay, in which part of OpenFOAM there is the copy. For example, this function calls do resides in the list class. This makes a lot of page faults. So one has to go there, take a look, okay, or there is the standard move function that doesn't work only on CPU. So we need to use our, let's say, move function provided by our memory pool that works on GPU. If I make it running, I basically remove a lot of page faults, and you can do it in step by step. So when at the end of this journey, you have to see basically no page faults in the CPU part. It means that everything runs on GPU, and you can do it step by step. You need to make it work in the first step. So let's have a look at the performance. The last slides. So we need to, so the target was to simulate this final stage wet turbine, okay, using steady state run simulations. The simulations runs from 5 to 8 hours on 2 nodes of Galileo 100. Which is our tier 1 cluster. Okay, the 100 node is based on 2 CPU Intel Cascade Lake with 24 cores each. Okay, the simulation converges smoothly to the condition provided by the end user. So the CPU runs as expected, and so the results were accepted by the customer. Okay, so we make the same on GPU. Okay, so we as before, we ported all the missing features on GPU, so overlap AMI, the moving rotate frame, so and then we perform the simulations on one GPU only. So basically 20 million cells runs a single GPU. That we have in the this case, the GPU are in our tier 0 cluster, so the Leonardo, which is in the 10th position of the top 500 list. So with a single GPU of Leonardo, NVIDIA A100, we get a time per iteration of about 2 seconds. Okay. If we take a look at this, the time that we get on the CPU part, for example, using 48 cores of Leonardo data center, remember that one node of data center has 112 cores. Okay, so using only 48 cores, the time per iteration is 8 seconds. If you move to 96 cores, the time decreases only to 6 seconds and 7. You see that basically increasing the cost doesn't scale too much, because the overlap AMI in the current implementation, as you find in its form of it, doesn't scale very well. Okay, because make it work in parallel using a distributed approach is very expensive and doesn't scale very well. Since we have only one GPU, there is no basically MPI. Everything is done in the shared memory of the GPU. Is you see that if we made a comparison CPU versus GPU, this number can increase a lot, because CPU doesn't scale basically. So and so if one say consider 48 cores, because or 96, this ratio is between 200 and 300. Or it can increase if you use more than cores, because it doesn't scale on CPU. Here also there are some slides where we have this performance background, where you see where we spend time. You see basically that the solution for pressure, energy, and momentum are not so expensive. So the most expensive part is the turbulence and the assembly of the momentum and energy. These are the most expensive part, basically the assembly part. The faster is the energy, because it converges very, very, very fast. And there is not too much differences in the performance background between a GPU run and a CPU. Probably here there are some little bit differences in that you spend a little bit more in turbo correction and in U assembly, but there is no too much differences. They are the same order of magnitude. Also in this case, where we compare the overlap AMI on GPU versus the CPU run using the mixing plane, and during this work, the mixing plane was not ported to GPU, so this is why there is mixing plane only on CPU. There is no GPU counterpart, because didn't have time to make it running on GPU. So let's say for the purpose of this work, let's assume that it works in the same way. They are different algorithms, but with the same target. And also the comparison, there is no too much differences also here. Yeah, CPU, GPU, different algorithms, but the breakdown is much more similar. Okay, conclusions, and then so we basically make simulations of compressible accelerated turbine on CPU successfully by integrating third-party libraries into OpenFOAM. We ported to GPUs these algorithms that are needed for turbo machinery, like overlap AMI, movie to rotate frame, using the SPUM approach that I show very briefly, using this lambda function, rewriting of the loops. And there are also some other parts, like the thermophysical models, some limiters that have been ported to GPU, that also required to make it simulation computer run on GPU. And we found that the cores to GPU ratio is in the same range as the incompressible cases. So we found that one GPU is equivalent to 200, 300, depends on the mesh and the boundary conditions, but for the incompressible case, we are in this range. We see that this number is also confirmed for this particular kind of simulations, where we have one GPU basically, but everything is on a single GPU compared to distributed CPU simulations for the CPU counterparts.
Everyone,